Okay, welcome back, AP Chem students. Here we go. This is our latest quiz. Quiz number 2, and actually quiz number 3. We took this right before spring break, and let's go through it. Okay, do this. Good. I'm going to pick as my acid conjugate base system the hydrocyanic acid. All right, so I'm going to click that one. Why can't I seem to click that? Why is nothing working here? Hang on. There we go. Okay, so I've got a pKa equal to 9.21. Technical difficulties here. Just be patient with me. 9.21, which means the Ka is equal to 10 raised to the 9.21 power. Okay, and that's good enough for us. Excellent. All right, so we start off. I've got a 0.2 molar solution of the acid. The acid is HCN. HCN is a weak acid, very weak acid. Look at that equilibrium constant, 10 to the minus 9.21, pretty small. HCN, however, does ionize slightly in water to produce H plus and cyanide ion. Again, to review, the HCN is the acid, the cyanide ion is the conjugate base. Good old ice table. We've got a weak acid problem here. I've got a 0.200 molar of HCN. Initially, I have 0 H plus and 0 CN minus. Let the system come to equilibrium. HCN concentration has to decrease by X. H plus increases by X. At equilibrium, I'm going to have 0.200 minus X, X, and X. You've seen this many, many, many times before. You can probably do this in your sleep. I know that the Ka is equal to H plus concentration at equilibrium times the cyanide ion concentration at equilibrium divided by the HCN concentration at equilibrium. And I know that at equilibrium, that's all equal to 10 raised to the minus 2.1 power. So plug in X for the H plus concentration, X for the cyanide ion concentration, 0.200 minus X for the HCN concentration. We're going to make the assumption that we've always made, that this is small relative to 0.2. So we're going to simplify that and just say that's X squared over 0.200 equals 10 raised to the minus 9.21 power. If you solve for X, I'm not going to show you that work here. If you solve for X, X is equal to 1.1 times 10 to the minus fifth. 2 sig figs because of the way that the Ka or pKa was given to us. That means the hydrogen ion concentration is equal to that, which means the pH is just the negative log of that, so the pH is 4.96. The pH makes sense. It's acidic, it's less than 7, weak acid, but it's not very acidic. The solution has a pH of about 4.96. Again, remember, if this was a strong acid, its pH would be down in the neighborhood of about pH 1. So definitely a weak acid, but enough acid that it makes the solution acidic. All right, that's just a weak acid problem. Hopefully you have that well under control. If not, you know who to see, you know what you need to do. Okay, part B. Okay, we're now going to add, I'm going to get myself a little bit more room here. We're going to take that solution from part A, that acidic solution, pH of 4.96, and we're going to add to it 1/10 of a mole of HCl. Okay, first thing you should notice, I hope, HCl, strong acid. Again, the first decision you have to make whenever you see an acid, is it one of your strong acids or is it a weak acid? Very important. We know that strong acids are completely ionized, weak acids are only partially ionized. So we're adding strong acid to a solution of a weak acid. So we have two acids floating around in here. We have HCN, our weak, very weak acid, versus HCl, our strong acid. Okay, completely ionized. HCl is the winner, overwhelms the HCN. HCl completely dissociates in H plus Cl minus. So if I have 1/10 of a mole of HCl and I've added that to a liter of solution, the H plus concentration is going to be equal to 0.100 molar. Does that make sense? Acid is completely dissociated. Compare this concentration to the concentration that we had up here. Wow. 10,000 times more acid from the HCl than from the HCN. Okay, so there's no doubt that the HCl wins the game here, and therefore my concentration of the H plus comes totally from the strong acid, and my pH therefore is at 1.0. Okay, notice that the change in the pH in this system, pH from part A, pH from part B, the final pH, minus the initial pH from part A, pH is 1 minus 4.96. The change in the pH is minus 3.96. Pretty large change in hydrogen ion concentration. Pretty large change in pH. Okay? So, we're going to go to part C here. Let me get rid of this. Now, we start again with the solution from question number 1. Okay, our original solution with the pH of 4.96. Now we're going to add 1/10 of a mole of sodium hydroxide. Sodium hydroxide, strong base, completely dissociated into sodium ions and hydroxide ions. We pay no attention to the sodium ions. We know that they are spectators. So now we know we're adding hydroxide. What happens in our solution? Well, our solution contains a weak acid. Weak acids react with bases to form the conjugate base plus water. So as we add base to our system, we are converting some of our acid into its conjugate base. Now notice, okay, my initial conditions were 0.200 moles, because I had a 1 liter solution of HA. I'm adding 0.0100 moles of OH minus, okay? I'm going to say initially I have 0 of this, and we've got plenty of water. Water's not going to be a factor here, so I'm not going to worry about the water, okay? Now, what's going to be the change? Okay, well, this reaction goes all the way to completion, so we're going to lose as much acid as hydroxide as we put in. The hydroxide ion concentration is going to go to essentially 0. The A minus concentration is going to, let me do this a little bit differently. My change here is going to be minus 0.100 moles, okay? My change here is going to be 0.100 moles, okay? My change here is going to be plus 0.100 moles, okay? And again, we're not going to worry about the water. It doesn't enter into it. There's plenty of water floating around here. Therefore, when this new system reaches equilibrium, my concentration of HA is going to be 0.100 mole in 1 liter, or 0.100 molar. This is going to be essentially 0. This is going to be 0.100 mole, okay? Therefore, notice what I've done. The acid and the conjugate base, have the same amount. They're both in a liter of solution. So the concentration of the acid, my HA, equals the concentration of the base, A minus, okay? And I use my buffer equation, the Henderson-Hasselbalch equation, that says pH of a buffer is equal to the pKa plus the log of the base concentration divided by the acid concentration. Plug in my Ka for my acid, hydrocyanic acid, is 9.21 plus the log of 1/10 mole solution for the base concentration, the same concentration for the acid. I've got the perfect buffer system. This ratio goes to 1. The log of 1 is equal to 0. pH equals the pKa equals 9.21. I have the best possible buffer system now. Okay, I created the best possible buffer. Notice the change from number 1. The delta pH here, again, pH in part C after the addition of hydroxide minus the pH in part A is going to be equal to 9.21 minus 4.96. My delta pH is a whopping 4.25. Let's keep that in mind. Solution 1 was definitely not a buffer system. Notice how dramatically the pH changed when we added either strong acid or strong base. Okay? All right. Good. I hope that makes some sense.